What are we doing? Mem buckets. All right, so we're going to come in here. So I have this mem buckets, and effectively I'm going to show you the picture here. If I go to Zybooks, this guy right here is a mem bucket. This guy right here is a mem bucket. This guy right here is a mem bucket. Got it? All right, so we're going to have this thing called data memory, which is going to be a collection of mem buckets. All right, so we'll right click, we'll say new, we'll say class, we'll call this guy data memory. All right, and data memory is going to have, now we probably need to, we're going to do this with instance methods because you do need to initialize it at the beginning. Yeah. So we're going to create a private, what do I call it? Mem bucket array called, you like that? Yeah, the buckets is good. It is. I always name them something like that. It's awesome. All right. Then we'll have a public data memory. What am I doing? This guy will take in a let's call it int byte size, number of bytes of memory, and we'll just assume that this guy must be a power of 4. So, or a multiple of 4. Okay, so for byte size has to be a multiple of 4. That way we, if it was going to be, for instance, mem size for this guy is 12. We have 3 4 byte buckets, 12. All right, so we would go ahead and say this dot the buckets is equal to new mem bucket array byte size divided by 4. That's going to be the number of mem buckets that we're going to have. So if I were to pass in 12, 12 divided by 4 is 3. This is going to create an array of 3 mem buckets. Something that looks like this. This is 3 mem buckets. Makes sense? All right, so then we're going to go ahead and we're going to fill up our mem buckets. Now, if we want to kind of be similar, it looks like the book kind of starts memory off at 5,000. Is that pretty standard? The book does it at 5,000. So let's just pretend like our first bucket is always location 5,000. So remember our mem buckets here are, they take only in a location, its position, and then they initialize the value to nothing, but also say it's not currently in use. So we'll say for int I is equal to 0, I is less than this dot the buckets dot length, I plus plus, this dot the buckets at bucket I is equal to a new mem bucket. And we need to give this guy a location, so I'm going to say int starting location. Well, let's call it int cur location. And we'll say we'll start at 5,000. So this guy will say cur location. Cur location. So I'll create a new mem bucket at bucket cur location. Go with location cur location. So the first mem bucket I create will be mem bucket 5,000. The next one I want to create is mem bucket 5,004. Then 5,008. 5,000, 5,004, 5,008. I'm building this guy. My data memory is this guy. He's a collection of mem buckets where each mem bucket has a location. Got it? So then I'll say cur location plus equals 4. So we'll add 4 to that guy. So it goes from 5,000 to 5,004 to 5,008 to 5,012, yada, yada, yada. All right, so data memory, when I initialize it, I'll say I want this much memory. It'll go ahead and initialize my memory, my street with all the memory addresses on it. I'm going to assume my very first available memory address is 5,000, and I'll go ahead and fill up my memory with a bunch of unused mem buckets that are labeled with their memory location. All right, so that's going to be my data memory. So now what we want to do is we want to have some abilities in here. We want to have the ability for a to request a mem bucket. So we're going to have a public int. Now, we could put error checking in here and kind of say something along the lines of, hey, what if I actually ran out of space in memory? But we're not going to do that. We'll just assume that your memory is always going to be big enough to hold all of our stuff. That way we don't have to have extra error checking in there, right? So if I put in, here, what? 50,000 times, well, I could have that math, 200,000. If I put in 200,000 bytes, I can store 50,000 integers. Is that going to be enough for us? Probably. Be okay with that. All right, so we'll just assume our memory is big enough. So what this guy is going to do is he's going to return the location, let's call it get address for new memory. All right, and we're going to assume we are always asking for 4 bytes or 32 bits. So this guy is going to return an int. We're going to get an address for new memory. And what this guy is going to do is he's going to loop through the buckets, finding the first bucket that is not currently in use. Actually, we can actually do a for each loop for this one if we want. That's what the cool kids might do. So we'll say for membucket mb dot the buckets. Yeah, oh, is this guy? Yeah, he's iterable. So if mb dot is in use, if he's not in use, we'll go ahead and return mb dot, oh, his location is private, so I need to generate setters and getters for this guy. So I'll right click. Fine, I'll just type it. Well, no. Oh, you don't want to type it. Okay, so is it source? Source, generate getters and setters. All right. I actually just want getters for these guys. Well, I want to get a we'll just cheat. We'll just do for all of them. Give myself getters and setters just in case I want them. All right. So now I have getters and setters for all of my guys. So now I can get the location. So I'll return mb.getLocation because I found an available location. But before I do that, I see mb.set in use to true. I found a mem bucket that's not in use, so I'm going to go ahead and set it as being in use and then return that location because the guy who asked me for that is looking for a memory address, or and I've given him one. Now this function does require me to return a value, so if I don't return a value here, he's going to be upset. So some people would do something like return -1, and -1 means I wasn't able to give you an address, something like that. You can also do something like throws new runtime exception. Can't, you be out of memory.
Why not all
All right, you be out of memory.
Why spelling so weird?
Huh?
I said why.
I didn't spell it weird. I spelled it cool. It's different. You be out of memory. Yeah. All right. So what does this guy do? He says, I'm going to get you a memory address for new memory. Get address for new memory. It's going to go through all my mem buckets and say, for each one of them, if this guy's not in use, go ahead and mark him for in use because I found a place for my guy, and I'll go ahead and return that location. And return makes a method immediately end. If I'm still kicking down here, that means I didn't find any memory that's not in use. So I'm either I am out of memory. Okay, it could be I'm really out of memory, or I have a bug in my code where I never actually released memory when I was done using it. Either way, I'm out of memory. All right, so this is a get address for new memory. All right, so now when we run into something that looks like int I or int x here, what assembly should we produce? We should produce an add I, a register number, a 0, and a location for that. I now have a dude that will give me a location, right? Okay, he's called data memory, and I can say data memory, give me an address for new memory. He'll hand me that location. Okay. Now, I also need a register that's not currently being used. So when I said add I into T0, that was presuming that T0, we assumed T0 was there, but what if I had 5 variables I was defining? It's possible T0 is not available, right? I need a fresh register. Right? I need a register that's not currently being used, and when I'm done using it, I'll hand it back. So I need a register manager. So we'll create a new class. This guy will be called we'll just call him a register. Register is going to have a private string name, and he will have a private int value. He'll have a private Boolean in use. Is that how I did it in membucket? I spelled it just like that? No, yeah. I didn't use all caps. I used. Well, we'll keep a standard. Okay, public register. This guy will take in a string name. Initially, we'll just create a register. And so that's kind of like our location for our mem buckets. And we'll say this dot name is equal to name. This dot value is equal to, we'll just 0 it. And this dot in use is equal to false. Then we'll have a public Boolean is in use. This guy will return this dot in use. And then just for convenience, I'll go ahead and generate my getters and setters. Source, generate this guy. Click, click, click. Ninja. Okay. So now we have registers. I'm going to go ahead and give myself a register collection. Let's call it that. So this is kind of like our data memory. But we're not actually, in this case, we're actually really talking to memory. This is our real memory. Where the register collection is more of this theoretical register names that we are able to use for our MIPS code that we're going to be outputting, right? Because we don't want to use T0 3 times in a row when it's storing 3 different values. We want to make sure it's available. All right, so this guy's really, his job is to keep track of what registers have already been used in the current scope versus what have I released and I can use again for something else. All right, so we're going to call this guy register collection. Okay, and for right now, we may have to expand on this a little bit as we get to the more complicated registers. Like we have, we do have a 0 register, which we'll actually need to have in here. So we probably want to have, let's just do, so we'll have a private register array called the registers. And then we're going to say public register collection. This guy is going to take in let's have it take in a num standard registers. So let's assume we have, what, like 20 registers? How many registers did they have in the book for our examples? Hardly any. So we had 0, so we'll just give ourselves, so I think the official MIPS definition is 32. We have 32 32-bit registers. Does that sound familiar?
Does that including 0 and I?
No, just the T's. I think we have 32 T's. So fine, we'll give ourselves 16 T's. So, well, whatever we pass in here is what we'll have. So we'll go ahead and we'll say, so we're going to have a 0 register. Let's just give ourselves a 0 register for now and then the T's. So whatever they pass in for num standard registers, we'll have one more than that. So we'll say this dot the registers is equal to a new register array of size num standard registers plus 1. Then we'll go ahead and say this dot the registers at bucket 0 is equal to a new register called 0. And I'm going to go ahead and, even though in the book they name our registers, with the $ thing before them, I'm going to go ahead and leave it without the $signs, because that's what will be, well, I was going to say that's what's going to be compatible with our MIPS CPU, but we're also going to have commas in here anyways, so we'll put the $signs in. So we'll make it official MIPS, and then we'll doctor it for ours if we have to. All right, so we'll have a new register called 0. Then that'll be bucket 0, and then we're going to have for int I is equal to 1, I is less than this dot the registers dot length I plus plus this dot the registers at bucket I is equal to a new register named $sign T concatenated with I minus 1. So that'll be T0, T1, T2, T3, because I starts off at 1 here. That makes sense for register collection? Yeah. Should have put smiley faces in there. I know. All right, so we're going to have a public we probably want to have a couple things here. We want to get register with a name. So if we ask for register 0, we ask, well, I'm not going to do that yet. So I want you to have to do some of this. We'll just add what we need for right now. So we're going to say public string get next, get next available register name. And this guy will go through I is less than this dot the registers dot length I plus plus, and he's going to find the first register that's not currently in use. I couldn't do a for each one on this because I wanted to skip the 0. I wanted to skip past the 0 register and just use register T0, T1, T2 because I'm looking for the standard use registers when I'm saying give me a free register that I can use for storing crap. All right, so we'll say if this dot the registers at bucket I dot is in use. If it's not in use, then what do I want to do? I want to set this dot the registers at bucket I dot set in use to true, and then I'll return this dot the registers at bucket I dot get name.
I have a question.
Mm-hmm.
I think this should not be this dot register dot length. It should be dot length minus 1.
No, it's less than it.
Okay.
You're probably thinking about adding in the I register later. Yeah, my implementation right now starts with a 0 register, and then all the rest of them are T's.
Yeah, you don't count the last number for the loop. Yeah.
Yeah, so this is less than the length.
So the name is
T0, T1, T2 as a string. That's this guy here. And then we'll throw new runtime exception. Let's see what we say here.
So what happens if you cannot find, if theoretically you cannot find available register in CPU?
Bad things.
Then you should try to.
Right, that's the whole reason different architectures have a different number of registers. It does limit the complexity of programs you can write on that. So a combination between your number of registers and the efficiency of your assembly code tells you how complicated the programs you can write on that architecture are without running out of registers. So you either have to write more efficient assembly code or you have to have more registers.
I see what you mean. So technically, that is how compiler works. Like based on your architecture.
Yep.
Technically, the compiler is different.
Yeah, a really efficient compiler can probably give you, allow you to write more complicated programs on a lower architecture than a inefficient compiler, because the inefficient compiler is going to be less optimized for the registers.
Yeah.
You know, it's just going to use registers left and right, and all of a sudden you're out of registers. All right, so get next available register. We're giving ourselves plenty, so presumably we're going to be writing simple enough stuff. We really shouldn't run into an issue here. But effectively, when we're trying to say, hey, I need to move a memory location into a register, what memory is available? What register is available? This guy's going to give you a register that isn't currently being used for something else. Okay? So, and then this throw runtime exception means that we're out of registers and bad things have happened. You can't write the program you're trying to write, either in terms of your architecture or you're writing crappy assembly code. You're just using registers left and right for everything. All right, so.
Do you actually use the word throw, or is it throws?
I think it's you throw an exception here, you can say this guy throws an exception up here. All right, so get next available register. We'll search through all our registers, find one that's not in use. As soon as it finds one that's not in use, it'll set it as being in use, and then it'll return the name of that register. Okay.
So, to put this in context, we'd be using this to, we're getting that register and then somewhere else we're going to be setting it to something.
Yes. Well, I mean, ultimately, we're trying to solve this one line right here.
Yeah.
This one line right here says, if you're defining a variable, what are we doing? I need a fresh available register. I need a fresh available memory address. Then I need to get the value of the 0 register and add 0 to 5,000 in this case and store it inside of this register. I want to output that line of code. And in order to output that line of assembly code, I have to find a fresh register and a fresh place in memory.
Isn't high-level languages supposed to be less, like, words than?
Yeah. Isn't this shorter? Isn't that shorter than this?
Yeah.
And then setting it to a value is these 2 lines. And that's just defining a variable. So you can imagine you start doing more and more complex things, stuff is going to start getting crazy, right? All right, so I'm going to give myself a class here called Compiler. Let's call this guy, I'm going to actually call him the Mips Compiler. Yeah, good enough. All right, and we're going to go ahead and create a constructor for this guy. Actually, before we do that, we're going to have private, and we have data memory. We'll call this guy the data memory. We'll have private register collection, the register collection. Then public Mips Compiler. We'll take in no parameters, and what we'll do is we'll set this dot data memory equal to new data memory, and data memory takes in a number of bytes by power 4. So what we say, 200,000. That'll let us store 50,000 ints if we wanted to. Good amount of memory, right? Okay, so 200,000 bytes is, so we divide that by 1,024, that's kilobytes, so it's 19.5K of memory. And Maddie over here was complaining that her laptop only has, what, 8 or 4? 8. We got 19.5K. Okay. Or 0.019 meg. Or 0.00018 gigs.
My computer does a lot more than just work with numbers.
We're going to do a lot more than work with numbers. This is going to be capable of doing whole programs.
Let's do it.
But the real thing is, can you remember?
And I bet you this guy can download Eclipse.
Do you really can remember that many integers in your brain?
What's this?
Do you think you can remember that many integers in your brain?
No, I can't remember my phone number. We already covered this. I'm washed up. I need to get all this knowledge out to the young people before I kick the bucket. This is an empty husk. All right.
Trying to downplay everything else.
That's it. That's what we're doing here. Okay, so data memory, we're going to say we're going to give ourselves 2,000 bytes of data. This dot, the register collection is going to be a new register collection, and register collection is going to take the number of standard registers is what we decided we take in there. So we'll go ahead and give ourselves 16 standard registers. So this will give us a total of 17 registers right now, a 0 register, and T0 through T15. Okay, so here's our Mips compiler. We have these two things. Now, I want to go into my, I'm lost. So we're in my register collection. We're going to say public int get, I'm in register collection. Get value by register name. This guy will take in a string name as a parameter. And he's going to go through all of our registers. So for register R in this dot the registers, if R dot get name dot equals name, if the register I'm currently looking at is the register I'm searching for, I will return R dot get value, the value of that register. And we'll say throw runtime exception register not found.
Where did you set the register value?
Huh?
Where did you set the register value?
I haven't set it yet. I'm not going to set it.
Oh boy.
Is our job?
That's going to be your job.
That's what I
This is going to be a simple assignment. But you're going to
finishing everything.
No. I'm going to be nice. You are only going to have to work for this. Defining a variable, setting its value. Your code should work for any number of those, but your code will compile C programs that only define variables and give them values. That's it. No logic, no less thans, no if statements, no loops, no functions. Just I can create variables. I can create the.
I can't even like picture this. Like, can you like?
Nope.
Wait a second. I saw the output of the compiler is the
I'm going to.
code, right?
Correct. So I'm going to show you the working pieces here in a second.
You know, there's a lot here. We're at a couple hundred lines of code.
Yeah, it's like this is nothing. Most of it's runtime exceptions. All right, so that's our Mips compiler there. So let's just go on a so our Mips compiler is also going to have a source reader. So we're going to say private source reader, the source. And let's say our Mips compiler will take in a string file name. And just because we might be interested, I'll go ahead and also store the file name up here. So we'll say this dot file name is equal to file name. We'll say this dot the source is equal to new source reader file name. And if you remember from our source reader took in a file name, read a bunch of stuff, and then did what? Right now it just outputs it to the screen. But what we actually want to do is we want to tokenize our input. Don't use that word. Don't use that word. I'll kill you. All right. If my file looks like this, I want to have an array of 2 strings. This is one of them. This is another one. These are lines of code. Okay? And for right now, we can presume that there's no empty spaces in our program or anything like that, so we don't have to account for that. So effectively, what I'm going to do in my source reader, I'm going to have a private linked list of strings called the high-level lines.
Code.
Let's call the high-level code. The high-level code. So in here we'll say this dot. We're going to import java.util.linked list. So I'll say this dot the high-level code is equal to a new linked list of strings. I'm using a linked list because I don't know how many lines of code are in my C program. Could be 3, could be 300, right? So I've given myself a elastic way of holding them. Now, rather than print them out here, what I'm going to do is I'm going to say this dot the high-level code dot add input dot next line. So I'm going to fill that array up with, or fill that linked list up with my instructions. All right. Now I'm going to say private int. Let's call it line pause. We'll set this dot line pause equal to 0, because the first line of code we're going to deal with is line 0. We'll say, at least for this version. So now I want to have a function public string get next line, and this guy will return this dot the high level code. Well, actually we probably want to do this only if we're not off the end of it. So if this dot line pause is less than this dot the high level code dot, was it size or count? Dot size. So if the line I'm looking for is somewhere in my code there, then I will return. Actually, what I'll say here is I'll say this dot line pause plus plus, so I'll add 1 to it. And then I'll return this dot the high level code dot get from this dot line pause minus 1.
I might be very out here, but this is reading from that test.c.
It's going to be. I'm going to show you that last piece here.
Okay.
We're super close. I promise. I'm going to return an EOF end of file when we finally run out of lines of code. All right, so now out here in my Mips compiler, I'm going to read in. I'm going to get a file name. I'm going to create my source reader, and then I'm going to go through and I'm going to say, we'll just do a couple of lines here. System.out.println this dot the source dot get next line. I'll just do that twice since we know we have 2 lines. Actually, I'll do it 3 times so you can see the EOF. So here in driver, I'm going to be creating a Mips C compiler instead of a source reader. I want to create a Mips C compiler. Call this guy the compiler. And he's going to be a new Mips compiler. So what does the Mips compiler do? Comes in here, he sets the file name, he creates a source reader. What does the source reader do? It creates a linked list, fills that linked list up with our individual lines of code. Then I set my data memory to be 200,000 bytes, 50,000 ints. I set my register collection to have 16 unique registers. Then I print out next line, next line, next line, next line. So I should get the int, what was it, int x, int, and then x equals 7, and then EOF means the end of file.
So all we're trying to do is print that out.
Yep. Proving that we're accessing those lines.
Wait, so that already works.
Yeah. So now what you'll have to do is for this line,
We want to actually store it.
you're going to do the logic that is, oh, you're one of those kind of guys, so I'm going to output assembly code that looks like this. It's always going to be add I, huh?
Print it to the screen.
Whatever, yeah, because this is just the first step, but here's the logic for it. It's always going to be an add I, right? If I see an int here in the first line, because we're only making this work for definitions and setting values. So basically, if the beginning of this guy is an int, I'm explaining in words the solution. All right? And you can just listen to the end of the video if you're zonked out already. If the beginning of it is an int, I will produce an assembly line that always starts with an add I that will give me the next available register, followed by a comma, followed by a register name 0. It will always be 0, followed by a comma, followed by the next available memory. And we already have tools for requesting the next available register and the next available memory.
Can the 0 register be hard-coded?
It already is. I mean, you're not running this code yet, so this is the name of a register. And we
Right,
already
do
have.
Do we need to use it as a name of a register if we always know that?
I see what you're saying. Dealer's choice. You can decide how you want to search for it. I'm going to say yes, you probably want to have it that way because in my register collection, when I get the value for it, if you give it the name of a 0, it's going to give you the 0. If that's valuable to you later.
No, I'm saying like, should I, like we have the register, should I get it as the register 0 or can I, like, am I pulling it in by like a function or can I?
You're not getting this from anywhere.
I'm typing
This
it
will
in.
always be that exact word
Okay.
for this guy.
Of course, you can say get.
It's always going to be 0.
Get 0 is I think it's sad.
Well, no, because that'll give you the value in that register. That's not what we have here. We have the name of the register.
If you get the register name, it will return.
But I didn't write that.
That's a lot of code you're gonna have to post.
I didn't write that. So you'll always output, if it starts with an int, you'll output an add I, next available register, comma, 0, comma, next available memory.
And we want it with commas.
Sure. If it's x equals 7, so if it's a variable name, followed by an equal sign, followed by a 7, what will I do? I will do an add I, next available register, a 0, the value we're loading, so we'll have to parse this. Then I'll store that in whatever's in that register. So, but I'm not actually storing it. I'm outputting SW, followed by the register that I just used, followed by a 0 offset by my where the thing was originally stored.
We're still actually storing things though, right?
You're storing things actually in
In the array or whatever it is.
yes, because you're going to need to access those values from it, but you're not going to be running the assembly code, but you should be able to.
Yeah.
All right, make some
No,
sense?
It's not in our compiler.
you have that test.c, so I have to get all that first line and transform that thing there, for example.
Mm-hmm.
So how I'm gonna get that value from the first line in test.c?
Source.getNextLine.
Okay.
And then if you want to see a couple other things, I'll do a system.out.println, and we'll say this dot the data memory dot get address for new memory. That should give us 5,000 the first time. And if I ask for it again, it should give us 5,004, 5,008. Then we'll do a similar thing for our register
That's always
collection.
getting the next one that's available.
Yep. And this dot the register collection, and this guy he'll get next available register name. So that should be T0 the first time, T1, T2.
Yeah, that's helpful too.
So
So we
5,000, 504, 508, T0, T1, T2
We have all the pieces.
of all the pieces for a working compiler.
So we're just doing.
For defining variables and giving them values. And I'm just going to zip up the source folder and put it on Slack. Sound good? Questions, comments, concerns, bribes, but also read the next chapter. Blaine, we wrote a C compiler.
Really?
Yeah.